Okay, so we jump straight to probability theory in section 2.1, discrete random variables. What's up with the discrete here? Are these random variables that are very good at keeping secrets? No. It's just terminology of discrete and continuous random variables. So we make this distinction when a random variable is defined only for specific values. For example, the integers or true and false, heads and tails. This is called a discrete random variable, roughly equivalent to categorical variables in the data chapter. In contrast, continuous random variables describe interval and ratio variables in the data. So, continuous quantities, any number, any real number, or over some interval. So continuous random variables, the math machinery is integrals. To compute probabilities, we need to integrate things. So this is a little more complicated, so we'll do that second. Discrete random variables, to compute probabilities, expectations, everything we're going to do in this section requires just summations. So this is what we'll start. Section 2.1 is the random variables of the simpler kind. And this will give us a easy place to give all the definitions. And simple examples like this that you can draw. So the key concept is the probability mass function. For each of the possible values of the random variable, how much weight, how much probability do we assign to that possible outcome? And there is an axiom called the Kolmogorov's axioms. There's two. That probabilities are always positive. That's the first one. And the second one is that the sum of these bars, if we were to add up the weight of the 6 possible outcomes together, the total is going to be 1. So it's just a normalization constraint. Okay. And we have 3 quick examples. A coin toss. The probability of heads is 0.5. The probability of tails is 0.5. So when you flip a balanced coin, when you toss a coin, it's going to be one of these outcomes. And the word balanced means that heads and tails have equal probability. This is what rolling a 6-sided die looks like. Each of the 6 possible outcomes has probability 1/6. And then to give something more fancy, a fancier example, here's the Poisson distribution. This is the Greek letter lambda. And the Poisson distribution needs a parameter, which corresponds to the mean of the distribution, where yeah. And here is the graph of it. When lambda is 20, you get a peak at 20, near 20. So probability around 20 are have more mass, and you drop off. Like it's very unlikely to see. So this context is a hard disk. This is a data center, and how many hard disks are going to fail per month this month? Okay, so you can read the details, and starting here, you start to see some Python function. So this is the math function, and this is the Python function. If you look carefully, so you have lambda to the h, so the parameter to the exponent h. You have e to the minus lambda, which is the exponential function, and then you have a factorial. So every time there is a complicated math expression in this book, maybe not every time, but I will, most of the time, they will be a Python equivalent. So if you feel uncomfortable with math formulas, look at them like impressionistic art or like alien symbols and focus on the code, because the code, the Python function fh is doing exactly the same thing as the math function. So if you type this into, if you open a new notebook, start new notebook, and type that in, you'll be able to follow the code examples. But for the purpose of this video, this is the easy mode. Let's go to this notebook that has all the functions filled in for us. So a little bit later, there you go. And then if you want to evaluate that function, let's evaluate it at 20. So that's the highest probability, the peak. Let's evaluate it at 21, a little bit less. 2021 drops down a little bit. So you never have to touch this math if you have Python on your side, right? So we are using these examples just to show the definitions. There's some exercises, but ignore those. I'm gonna send a better document, the updated version of these. They're pretty good. It's just I'm gonna send them as a separate PDF. Okay, so then there are some other, once you understand the basic concepts of probability, there are some useful add-ons, things we compute from the probability. Every random variable, we can describe it as a cumulative distribution. So instead of, this distribution tells you the probability of each outcome, and the cumulative distribution is a running sum, running total, like up to 10. What is the cumulative probability of 10, 9, 8, 8, 8, all the outcomes up until a certain value? So it's going to be strictly increasing, right? Because we're adding more and more outcomes. So it starts at 0 and it keeps growing. It's still a function of the upper limit, how many of the outcomes are included, and it always ends up at 1. So the shape here, you see there's a bunch of jump steps, and each jump happens at one of the values where the function is defined. So the information in the cumulative distribution is exactly the same as in the probability mass function. CDF, cumulative distribution function. Many things in probability work out better if we use the CDF. So that's why you need to know it. It's a very nice definition. The inverse cumulative distribution is this function. If you look at it as this is the input, you say how far do I have to go to get 0.6 probability, and it will be 21, I think. So you see it's this exact same function, but flipped through the diagonal, through the, okay. And the other concept, so, is the notion of expected value. So far we talk about probabilities just on their own. Often we're not interested just in the random variable x, but some function that depends on x. I'm using the example like for different outcomes of the die, you win a different amount. So the winnings function. And for that, given this notion, so given a function w that depends on the random variable, we can ask what is the expected value. So x is not a number, x is a random variable. So x can be 1 through 6 with different weights. So for each possible winning, we multiply it by the probability of this outcome. So this is called the expected value of the function w. and it's very, the probability came from gambling. So this is how much you're supposed to win at a game. It's very related to actual winnings. So the W is not a coincidence here. Example, the mean of a distribution and the standard deviation and the variance, and the square root of that is the standard deviation, are defined in terms of expectations. So given the randomness of x, what is the expected value of x? So, what number will x be on average? So that's the notion of a mean of a distribution. You're already familiar with the mean of a data set, of a sample, but here we're talking about the mean of a distribution. So if we go back to the graph, each of these possible outcomes has a different probability of occurring. And, these are less than 20, these are greater than 20. And we say, what is the average outcome? It's going to be 20, because, half of these weights are pulling you towards greater than 20, and half of them are pulling you towards less than 20. And that's the definition of a mean of a distribution, is just like for data, where is the place that would balance? Half the weight of the probability mass function is on the left, and half the weight is on the right. So there you go. Very important concept. We'll see it hundreds of times in the rest of the book. More examples to reinforce the concepts. Some formulas. And we're done. Okay, so the section closes with more computational models. So you have the notebook, so you have a bunch of examples already, but in the book I explain how to use the probability models at the end of the section. So this is the key player here. The SciPy Stats module is amazing. You have everything, every probability function we're going to use in this book. It is defined here, and you just create an object. I use the convention to always call random variables RVX, and you can compute the probability mass function, the cumulative distribution, the inverse of the cumulative distribution, all the properties of the random variable, generate random variables, compute expectation. Basically everything we did in this section is available with as methods on random variable objects. And to conclude, we show some calculations with the Poisson model. Instead of doing it manually here, like I did in the notebook, we do them using at the end we repeat all the calculations using the Poisson model. Same graphs, same results. That's it. So this is a little foreshadowing for later chapters. I'm not gonna talk about it. This is what I've cut out as the first contact with probability theory for you. I hope it makes sense. And for the next sections, we'll go to multiple random variables and continuous random variables. It's a bunch of probability to come. But now is the time to really read the definitions, because these concepts, the concepts from this section apply for the rest of the chapter. If this section if there's anything unclear in this section, you need to please ask in the forums, ask me by email, you need to make sure this section is super crystal clear, hence the exercises. There'll be lots of exercises. All right. See you all on Friday. Bye.